Welcome back to the Math Professors. Today I'm going to cover directional derivatives, and I want to start with a relationship to a derivative you saw in Calculus 1, move it to the partial derivatives that you've already seen in Calculus 3, and then finally see how all this is related so we can find the directional derivative. So in Calculus 1, what we know is the derivative is at that point would be the slope of the tangent line at that particular point, and we know it's defined by the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h. Now remember, it's essentially the change in y's over the change in x's. So if I have some, x over here, I'm going to have some f of x right there. And if I look at this particular point, I can find, the slope of that secant line. And as x gets closer to x naught, what's going to happen is this secant line is going to transform into, this tangent line. So really the derivative is just the infinitesimal smallest point from x going to x naught of really just your rate of change of your slope. So, and we can see the x naughts cancel, and that's why we get this. So really this is essentially the idea of just, rise over run, just over a very infinitely small run. Now, when I want to look at the partial derivative with respect to x, what we have is we now have this three-dimensional function that kind of looks like our magic carpets. And what I'm trying to do is I'm trying to find the derivative just, in the x direction at the point x naught comma y naught. So right here in its domain, just like I have the domain here, that's going to be x naught. Well, the domain of a three-dimensional function is going to be all the xy planes, so this is going to be some point x naught comma y naught. Now, if I want to go in the x direction, I need to go in this I direction. And when I do that, I can see that it takes this magic carpet and it's going to slice it, at this constant y naught in the direction of x. So it's going to slice it right here. Now, if we just identify the slice, when I pop this thing up to that point of f of x naught comma y naught, I can see that this is essentially going to be the slope of the tangent line at that particular slice in x naught. Now we can see how this looks like for the definition, that what we do for the partial derivative with respect to x is we hold y constant. That's why, remember, I'm taking this slice, across this y right here, which is why I get this slice. But I'm going to do this at the particular x naught. So again, I'm going to have an x and x minus x naught. I'm going to slide those points closer just like I do here. Okay, so now what we can see is it's going to be the limit as f of x naught plus h comma y naught minus f of x naught comma y naught over h. And I can see only the x's are changing. And I can see that y is holding constant, which is why we call this the partial derivative with respect to x. It makes it go in the x direction. Now, very similarly, if I want to do it in the y direction, I want to slice this way. What's going to do is it's going to take our magic carpet. It's going to slice this at that constant x, which means I'm only moving in the y direction, or moving in this j direction for this slice at that point x naught comma y naught. And then when I look at that definition, I can see that it's going to be the limit as h approaches 0 of f of x naught comma y naught plus h minus f of x naught comma y naught all over h. And we can see only the y's are changing and x is holding constant. So again, you can see the definitions are very, very similar. Now, when I want to find its directional derivative, I don't just have to go, say, in the x direction or just go in the y direction. I can go in any unit vector's direction. So we'll just call this the unit vector u, and I'm going to say some u1i plus u2j. So what I'm going to do is I'm going to slice our magic carpet in that u direction, which is going to look like this. Now at the point, f of x naught comma y naught, when I pop that up to here, I get that f of x naught comma y naught. What I'm again is going to get the slope of the tangent line at that particular point. So this is kind of coming out at us, directly in the direction of the pink thing. And when we go to our definition, what we can see is the derivative of f with respect to s. They use s as a parameter as opposed to h, but really it's still going to 0. So this is going to be f of x naught plus su1 comma y naught plus su2 minus f of x naught comma y naught over s. Notice that both the x's and the y's are changing in this case, which is why we call this in the particular direction. Only x is changing here, that's why it's a derivative with respect to x. Only y is changing here, that's why it's a derivative with respect to y. But in this case, they're both changing, so that's why this is going to be the derivative with respect to this u vector. And I wrote this in notations that we might not, be used to, that this is the partial derivative of x in the I direction at p naught. Or I could say the derivative with respect to x of f evaluated at p naught. Very similar, if I'm taking the partial derivative of y, it's going to be essentially the derivative of f with really it would just be this derivative of f with respect to y, but in the I direction at p naught, or I could say dy of f at p naught. And then we also know that this is going to be the derivative of f with respect to s. We're using s as our parameter because we're using this this line, this curve s, which is here at p naught. So I could say du of f evaluated at p naught. So trying to get you guys the same notation to see that we're really doing something very similar. So I should say, I guess if I really wanted to make this correct, instead of saying x and y, I really should say, I and j, because this is the direction for which we're moving. Okay, so now that we have the idea, I'd like to use the limit once, and then we have a much better way, or actually I'd say a more simple way of finding its directional derivative using a property of the chain rule. So here I have a function. My magic carpet, my blue thing, is going to be f of x comma y is x squared plus xy. I'm going to pick the point x is equal to 1, 2, so I'm going to go over 1 in the x, and I'm going to go 2 in the y. And I need to go in terms of this unit vector u. Now, I said it has to be in terms of a unit vector, and we can see that I and j essentially are unit vectors because I is going to be 1i plus 0j, j is going to be 0i plus 1j. So just like these had to be unit vectors, this does as well, and we'll kind of see that when we show the chain rule why the unit vector needs to be. We don't want to stretch it. Is essentially we want to just change its direction. Okay, so what I know, it's going to be f of x naught plus su1. So what I need to do is, I'll write it in this f notation first. Well, x naught is going to be this 1 plus s, and u1 is going to be the ith direction, so this is going to be, 1 over root 2. Comma, y naught is going to be 2 plus, su2, so s times u2 is going to be this, which is going to be 1 over root 2. And then minus f of x naught comma y naught, and this is all going to be over s. So what I'm going to do is I'm going to, plug this into the f function. I'm going to evaluate the function at these two inputs. So remember, this is the x location, this is the y location, so I'm going to have an x squared, so 1 plus s over root 2 squared, there's x squared, plus now I'm going to have x, which is going to be still this, 1 plus s over root 2, times my y, which is 2 plus s over root 2, and then minus, in this case, x is going to be 1 squared plus 1 times 2. And this will all be over s. Now we're just going to go ahead and expand these things. So this is going to be the limit as x approaches 0 of foiling this is going to give us 1 plus, well, outside and inside is going to give me 2 of these, so plus 2s over root 2, and then plus this thing squared, so this is going to be s squared over 2. Plus, when I FOIL this, 1 times 2 is going to be 2. Outside is going to give me 1 of these s over root 2's. Inside is going to give me 2 of those, so this is going to be plus 3s over root 2. That's outside and inside. And then finally, the last is going to be the same thing. I'm going to have s squared over 2. Minus, now 1 squared is 1 plus 2, so this is going to be minus 3. And this will all be over s. Now something simplified. We can see 1 plus 2 minus 3 is 0. I can see that I have a 2s over root 2 and a 3s over root 2, so this is going to be the limit as s approaches 0 of 5s over root 2. And then I have an s squared over 2 plus s squared over 2, which is just going to be plus s squared, and this is all going to be over s. Now, since all these terms have an s in it, I can factor that s out. And I'm going to get 5 over root 2. I should make that look more like a 5 instead of an s, plus s. And this is all going to be over s. The s's cancel. And now I can evaluate this expression at 0. So 5 over root 2 plus 0 is simply going to be equal to 5 over root 2. Now I want to leave that up there because I want to show you guys how to find the directional derivative using the chain rule, which is going to make this 5 over root 2 show itself very quickly. So let me erase and I'll come right back. So here is the quicker way. If I want to find the derivative of f with respect to s in the direction of u at p naught, so what I have is I have a p naught here again, which is going to be, x naught comma y naught. So this is our p naught. And it's going to be in the direction of this u. Now, I can see that the line or this curve that actually is going to be in the direction of u, it would be r of s because we're using s as our parameter here. It's going to be, x naught comma y naught is where we're going to start at, and then we're going to go in the direction of u, so u1, u2, s. So I can say x is equal to x naught plus u1s, so y is equal to y naught plus u2s. So if I want to use the chain rule here, what I know is, since this is going to be the derivative with respect to a parameter s, I have to first take the derivative of f with respect to x. So this is going to be df dx. And then I have to multiply the derivative of x with respect to s. So this is dx ds. Plus, this is going to be, again, the derivative of f with respect to y multiplied by dy ds. And we know that's the chain rule. We can see that it kind of simplifies, is that, this still gives you df ds, this still gives you df ds, and I'm taking care of both components x and y. Now, I'm going to have to, evaluate each one of these pieces at p naught, and then x comma y is going to be, going through that point in that particular direction. Okay, now what I see is the product of the product of two things connected to a sum, and what this is nothing more than a dot product. That one I have, I'm going to write this in this way. One I have, df dx, comma, df dy, or if you like the ijk form, I can say df dxi plus df dyj. And this is going to be, evaluated at p naught, so this would be evaluated at p naught. And this is going to be dotted with dx ds, dx dy, so I can say, dx ds, dy ds, or if you prefer, again, the jk notation, dx dsi plus dy dsj. And this is nothing more than the derivative of that curve r of s, which really is just the velocity curve, which is going to be the direction for which we're going. So, and these are going to be the partial derivatives. Now, what we have for a name of these things is your vector that is built of the partial derivatives has a special name. We actually call that the gradient of f. It's where the x component is a partial derivative with respect to x, and the y component is a partial derivative with respect to y. If you have more components, then it's going to be the partial derivative with respect to z, and then so on for every single component. And this is going to be evaluated at p naught. And what we have here is if I want to take the derivative of x with respect to s, I can see that x is going to be, this curve right here. So the derivative of this thing with respect to s, being the parameter, is just going to be u1. So this is going to be, dotted with, maybe I'll erase this. This is going to be equal to, let's write it this way and I'll do that next. So df dx, comma, df dy, evaluated at p naught. And this is going to be dotted with the vector, well, the first one, the derivative of x with respect to s is going to be u1, and the derivative of y with respect to x is going to be u2, which is nothing more than the velocity vector, which is just the direction of that particular thing. So what we have here is this is called the gradient of f, evaluated at p naught, dotted with its direction. Now, and actually what I'm going to do is I'm going to write this as just u. Now note, u has to be a unit vector, so where u is the unit vector in the direction. Okay, so this is actually a much easier way to be able to pull off something like this. So what I can do is I might just squish this in the margin right here. No, I think what I'm going to do is I'm going to write this here, and then I'm going to take its derivative and show you I get exactly the same thing. So let me put this up here, and then I'll do the derivative below it. All right, so let's find the directional derivative of this thing using our new definition. So our start is we need to find the gradient of f. Well, the gradient of f is nothing more than a vector function where its components are the partial derivatives. So, this is going to be the derivative of f with respect to x, comma, the derivative of f with respect to y. So the derivative of this with respect to x is going to be, the first component is going to be 2x plus y. And then the derivative of this with respect to y, well, this is 0, this is just going to become x. So that means the gradient of f evaluated at our point p naught, so this is going to be evaluated at 1, 2, is going to be, well, everywhere there's an x, there's going to be a 1, and everywhere there's a y, there's going to be a 2. X again is 1, so what we're going to get is we're going to get this direction of 4, 1. Okay, now what I have to do is, we know that the unit vector u is already written as this pink thing, so this is going to be, so that means the we'll say du of f evaluated at p naught, which is what this is going to be equal to, the gradient of f, which is going to be this thing. We have 4, 1, dotted with our unit vector, which is going to be 1 over root 2, 1 over root 2. That's our u vector. So let's do the dot product. This is going to be 4 times this is going to be 4 over root 2, plus 1 times this, which is going to be 1 over root 2, which indeed gives us 5 over root 2. Which is why we actually much prefer to use this definition as opposed to this definition, because look how fast that is. So one more kind of explanation of how the directional derivative is actually related to the partial derivatives, and I just want to show you that. So the directional derivative of f in the direction of u is the gradient of f dotted with u. Now, really, what I want to do is I want to show you that we can directly get the directional derivative of f in the direction of u is the gradient of f dotted with u. Now, I can relate this directly to the derivative with respect to x, the partial derivative with respect to x, and also the partial derivative with respect to y. So what we know is that this is going to be equal to, df dx, comma, df dy, and this is going to be dotted with, u1, comma, u2, assuming that, this is a unit vector. So if I want to find, df dx, well, essentially what I know for this is our unit vector would have to be, 1i plus 0j, or I could write this as 1, 0. And if I want to find the derivative of f with respect to y, well, that would mean that my unit vector is going to be 0i plus 1j. Or I can write this as 0, 1. So let's find that derivative of u with respect to f. Now this is going to be in the direction of I, so let's do this in the direction of I instead. Well, this is going to be equal to the gradient of f with respect to, the gradient of f. And what I have to do is I'm going to dot it with this thing. So this is going to be dotted with 1, 0. And what we'll get is we're going to get df dx times 1, multiplying those, plus df dy multiplied by 0, and that term goes away. So this is nothing more than df dx. And then very similar, if I want to find df dy, let's say the derivative in the j direction of f, which is going to be just df dy. Well, this is going to be the gradient of f dotted with 0, comma 1. And we can see that df dx times 0 plus df dy times 1, that term will go away, so this just gives us the derivative with respect to y. So your directional derivative is more of an expansion on this thing. We don't just have to go in the I direction or the j direction. We can really go in any direction. So if you like the content, please subscribe.